Well, hi there sports fans, and welcome to another exciting edition of Physics 12. This time it's lesson 1.4 with constant acceleration equations. So we're now actually going to look at some of these equations that we can use when we're dealing with constant acceleration. Now what we've looked at so far is we've looked at displacement, which is a vector, and we've looked at velocity, which is a vector, and acceleration, which is also a vector. And the comparative scalar quantities to displacement would be distance, and for velocity would be speed. So the corresponding scalar quantities for these two, for displacement, is displacement and velocity is distance and speed. We don't really have a corresponding scalar equivalent for acceleration because acceleration always depends upon direction. And so we don't really deal with anything in terms of corresponding to a scalar with acceleration. So we don't have to worry about that. So these quantities right here, all too often we use these terms interchangeably in our vocabulary, but these are separate entities and we need to be able to keep them straight in our minds. And so as you're learning these, you need to recognize the difference between them, because when you're problem solving, you need to know for sure whether you're dealing with a vector or with a scalar. And so these are all very, very different quantities, and you need to be able to keep them straight in your mind when you're problem solving. All right, these vectors, which are very distinct, in other words, displacement is one of those. Displacement is very distinct from velocity, which is very distinct from acceleration, although they all relate in some way. However, you need to understand that they are all different entities. Now, they can be evaluated with certain equations, and you'll see that quite often more than one of them appears in the same equation. So in that way they are related, and we can work with them in order to find quantities that we need to determine. In other words, are unknown. So the first equation is when the acceleration is 0, then we can simply use this equation right here, where the displacement equals the velocity times the time. But that's only when the acceleration is 0 can you use that equation there. So when the acceleration is not 0, then that's when we have to, we will have a changing velocities, and we need to account for that. And so one equation that we use is this one here. And so if you have a certain amount of acceleration over a certain period of time, then your velocity is going to change. And this equation reflects that. Also, we have acceleration, then also will be the average velocity times the time. So that's another equation that we can work with, and we've dealt with average velocity before. So if you need to refresh yourself on average velocity, then you can look back in your notes and find that there. All right, so these two equations here, from these two we can derive other ones. We can derive two other ones that I'm going to introduce to you right now. And the one is the displacement. So displacement equals velocity times time plus 1/2 acceleration times time squared. And you may have seen these before in your last year's physics course. And here's the other one that I'm going to introduce to you right now. Final velocity squared equals the initial velocity squared plus 2AD. All right, so those are 4 equations there that we're going to work with. There are others, and obviously there's a lot more formulas that we will be dealing with in this course throughout the year. But for the next bit, we will work with these, and we will be doing problem solving with them. So then, in terms of problem solving, there are certain steps that you should go through, which will help you in getting to a solution the most direct way. So number 1 is determine what you are given. So write down your givens. What do you need to know? What are your unknowns? What do you need to find out? And then from there, find a formula like one of the four that we just looked at, that will provide the unknowns. Okay, so look at one of those equations, which will help you find some of the unknowns. Whether it could be more than one. You might have a couple of steps in the problem in order to find a solution. And don't forget of course, your diagram. Don't forget your diagram. I'm going to be harping on this all year, folks. So please get in the habit of right away, when you're problem solving, do a diagram. All right, so let's look at an example here. And so here's our problem. We have a bungee jumper who's moving down at 5 meters per second, and then ends up moving up at 8 meters per second 2.0 seconds later. So we want to find the acceleration of this bungee jumper, and when we get the correct solution, we'll see that it is not 1.5 meters per second squared, and we'll explain why that is. So with problem solving, first of all, start with your diagram. Okay? Always just start with your diagram. So here's our object, or here's our bungee jumper. Okay, this is the best artistry that you're going to get from me this year. And so just get used to it. Here's our bungee jumper. The initial motion is in the down direction, and we're told that the initial velocity is down at 5 meters per second. And then we're told 2.0 seconds later that the velocity of that same bungee jumper is now 8 meters per second in the up direction. All right, so we'll write down what it is that we know. The initial velocity, now here's where you have to be aware of your pluses and minuses. And if your diagram will help you in that regard. So what we're going to do is we're going to make the down direction, we'll call that negative, and the up direction, we'll call that positive. So that's why the initial velocity is minus 5 meters per second. The final velocity is positive 8 meters per second. And the time is 2.0 seconds. All right, so there's our diagram, there's the information. And here's the equation then, or the formula that will help us get our unknown, which is the acceleration. So we want to find the acceleration. All the other things in this equation we have. We have final velocity, initial velocity, and we have time. And we need to find the acceleration. All right, so I'll just put the numbers in. Final velocity is 8, initial velocity minus 5, and time is 2. Then we'll isolate A. So we'll move the minus 5 over here, and then we divide both sides by 2, and we get the acceleration is 6.5 meters per second squared. Again, with acceleration being a vector, we need to indicate its direction. Now, as you noticed, when we worked with these equations here, we usually just drop the vector signs because we know we're dealing with vectors, and it just becomes a hassle. We kind of get lazy. We just want to don't want to bother putting the vector symbols on there all the time, and that's perfectly fine. But your final answer, make sure that you indicate direction for your final answer, and we'll write it this way. So the acceleration then is positive 6.5 meters per second squared, and just like we use the I symbol for the x direction, we use the J symbol for the y direction, so this would be your final answer. Okay, so there's a simple example for you to get started with, and we will do some more of that in class.